In this session, we are going to examine the physical and chemical properties of an alkane. We define alkane as a saturated hydrocarbon whose carbon atoms are arranged in a chain. And alkane is the simplest type of organic compound, and actually alkanes are members of a larger class of organic compounds called the hydrocarbons. And hydrocarbons are compounds that contains only carbon and hydrogen. In this slide, it shows a four classes of hydrocarbons along with the characteristic type of bonding between carbon atom in each class. So we will focus our attention first in alkanes. So alkanes are saturated hydrocarbons. That is, they contain only carbon-carbon single bonds. Saturated in this context means that each carbon in the hydrocarbon has the maximum number of hydrogens bonded to it. A hydrocarbon that contains one or more carbon-carbon double bonds, triple bonds, or benzene rings is classified as an unsaturated hydrocarbon. That means if alkanes has a single bond, that means it is said to be saturated because it complies already 4 covalent bonds. Covalent bond between carbon and hydrogen here. Another covalent bond between carbon and hydrogen on this portion, and carbon and hydrogen on this portion, and a carbon-carbon single bond. So that means it is saturated. But on the other hand, we have alkenes, alkynes, and arenes, which are considered as unsaturated hydrocarbons. But we will focus our attention first in alkane. Soon, we will discuss alkenes, alkynes, and arenes. Oftentimes, we refer also alkanes as aliphatic hydrocarbons because the physical properties of the higher members of this class resemble those of the long carbon chain molecules, which we can find in animal fats and plant oils. So it is from the Greek word alethar, that means fat or oil. In this slide, methane or the CH4 and the ethane, which is the C2H6, are the first two members of the alkane family. This figure here shows us the Lewis structure and the ball and stick model for these two alkanes, the methane and the ethane. So the shape of methane is tetrahedral. Each carbon atom in ethane, on the other hand, is also tetrahedral. So, and the bond angles in it are all approximately 109.5 degrees. Although the three-dimensional shapes of larger alkanes are more complex than those of methane and ethane, so the four bonds about each carbon atoms are still arranged in a tetrahedral manner, and all bond angles are still approximately 109.5 degrees. The next members of the alkane family are propane, butane, and pentane. So here, it shows the ball and stick model of propane, butane, and pentane, also the line angle formula, and the condensed structural formula. Usually, these hydrocarbons can be drawn as a condensed structural formula, which shows all carbons and hydrogens. But they can also be drawn in a more abbreviated form called the line angle formula. So in this type of representation, a line represents a carbon-carbon bonding. And a vertex here represents a carbon atom. So in this context, we have here 1, 2, 3. That means it has 3 carbons. Okay? And the line here from this point to another point will be the bond between carbon and another carbon here. So a line ending in space represents a CH3 group. Again, a line ending in a space, this one and this one, is represented by the CH3 group, or we know as methyl group. To count a hydrogens from a single line angle formula, you simply add enough hydrogens in your mind to give each carbon its required 4 bonds. So usually chemists use line angle formulas because they are easier and faster to draw than the condensed structural formula. So structural formulas for alkanes can be written in yet another condensed formula. Just like, for example, the structural formula of pentane. Okay, this is propane, this is butane, and this is pentane. Okay, so for example, we have the structure or the structural formula of pentane that contains the CH2 here, or the methylene groups in the middle of the chain. Okay, we have 3 methylene groups here. We have 3 CH2 and we have 2 CH3 on both sides of the angle. Now, how do we name alkanes? Ideally, every organic compound should have a name from which its structural formula can be drawn. For this purpose, chemists have adopted a set of rules established by the International Union of Pure and Applied Chemistry, or IUPAC. The IUPAC name for an alkane with an unbranched chain of carbon atoms consists of 2 parts. Number 1, a prefix, which has the number of carbon atoms in the chain, and number 2, the suffix ane or ane, shows that the compound is a saturated hydrocarbon. This table here gives the prefixes used to show the presence of 1 to 10 carbon atoms. As what you observe, if the number of carbon atoms present in your compound, it gives you specific prefix, which is meth if 1 carbon, F if 2, prop if 3, but if 4, pent if 5, hex if 6 carbon atoms, hept if 7, oct if 8, non if 9, and dec if 10. Next slide, we'll focus on the IUPAC names of alkanes with branched chains that is consist of a parent name that shows the longest chain of carbon atoms and the substituent names that indicate the groups bonded to the parent chain. For example, we have here the 4-methyl octane. 4-methyl octane, if we have the condensed structural formula, the line angle formula. Okay, so the 4-methyl octane here, we will locate first the parent chain, and the parent chain is the longest chain of carbon atoms. So of course this is the longest chain. Okay, while when we are talking with the substituent name, this is the substituent. The substituent is the groups bonded to the parent chain. So we will count the number of carbons present in the parent chain, in the longest chain of carbon atoms. Here, number 1, 2, 3 carbon, 4, 5, 6, 7, 8. So, it is composed of 8 carbons in the parent chain. Again, go back to our previous slide. Since it's 8, so the prefix is oct. Okay, since it's oct, so we have the oct here. Okay, then we add the ane, which is the suffix that may show us that it is a saturated hydrocarbon. So the longest parent chain is octane. But as what we observe, we have here, which is the substituent or the branched chain of the parent chain. So we will name this one the substituent, which is CH3, as methyl. And we will locate where this methyl substituent is attached. What carbon this methyl is attached? In the carbon number 4. Thus, we name this structure or this compound as 4-methyl because the methyl is located in the 4th carbon of the longest chain, which is octane, containing 8 carbons. Now we have the alkyl groups. When we are talking with alkyl group, it is a substituent group derived from an alkane by removal of hydrogen atom. Commonly, it is represented by the symbol R or the R group. And alkyl groups are named by dropping an ane from the name of the parent alkane and adding the suffix YL. Okay? For example, we have methyl here. Supposed to be, it is methane because it has 4, okay? It has 4 bonds. One bond capable of bonding to another atom, and we have 3 hydrogens. It is methyl. Eth meaning you have 2 carbons. We drop the ane, we change it with YL, that's why it's ethyl. Here, propyl. Okay? So propyl means that it has 3 carbons. 3 carbons. We supposed to be, the name is propane, but we drop the A and E and change it with YL. That is why it's propyl. This one here, we have the isopropyl. Propyl siya because it has 3 carbons. But this iso here signifies the location of this one. Okay? Butyl because it has 4 carbons. But supposed to be the alkane is butane. But we drop the A and E and change it with YL. In naming compounds using IUPAC names, we have rules. Okay, so we have rules in naming alkanes. And number 1, this is the name for an alkane with an unbranched chain of carbon atoms consists of a prefix showing the number of carbon atoms and the ending is ane. That means we need to locate the longest parent alkane. Okay? For example, we have here 2-methyl propane. The longest chain of carbon here is prop. Okay? Because it composed of 3 carbons. 1, 2, 3. So 3 carbons. So the name will be propane. That's for number 1. For number 2, for branched chain alkanes, if there is branching alkanes, longest chain of carbon atoms is the parent chain and its name is the root name. And we name the number each substituent on the parent chain used by a hyphen to connect the number of the name. So, in this example, the longest chain here is propane. 1, 2, 3. And this is the substituent that is attached to carbon number 2 of the longest alkane. Then therefore, we number it to methyl propane. Lastly, if there is one substituent, number the parent chain from the end that gives the substituent the lower number. So meaning, if the substituent is located in this portion, for example, we start giving the lowest number to this carbon. Carbon number 1, carbon number 2, carbon number 3, 4, and 5. That's why the correct name of this compound is 2-methylpentane, not 4-methylpentane. Why? Because it gives the substituent the lower number here. Not here. We don't give the lower number of carbon from here because the substituent is located here. How about if the same substituent occurs more than once. That means it occurs twice. First, you need to number the parent chain from the end that gives the lower number to the substituent encountered first. So again, the same also with our previous slide. The first, of course, the lower number, we assign the lower number if the substituent is near this portion. So, also, we indicate the number of times the substituent occurs by a prefix di, tri, tetra, penta, hexa, and so on. So if it's twice, it occurs twice, then therefore we have di. If thrice, of course, tri. Okay? So also, we use a comma to separate position numbers. Just like, for example, in this compound, we have the condensed structural formula, and we have the line angle formula. So this is 2,4-dimethylhexane. Why? Because, again, we need to count the longest parent chain. So this is the longest parent chain, and it has 6 carbons. Thus, we name it as hexane. Now, how many substituents? Here, 1 and 2. So the substituent, of course, that is CH3. That means it's methyl group. So it occurs twice, then therefore this is dimethyl. 1, 2, that means it's di. So the name is methyl, and we add the prefix di. That is why it's dimethyl. And now you give the position of the methyl substituent. Where? In the carbon number 2 and carbon number 4. Why is it the name of this compound is 2,4-dimethylhexane? Because, of course, we count the number of the longest parent chain, or the number of carbon of the parent chain, and we assign number 1 here, or the lowest number here, near the substituent. Okay, so let us try to look into this. If we start numbering here, that means 1, 2, 3. That's the substituent occurs in the 3rd carbon. But if we start here, the substituent is attached in the carbon number 2. Based on the rule, here, number the parent chain from the end that gives the lower number to the substituent encountered first. So that means this first substituent encountered first near this one. So that is why we start to count here, not on this portion going to this portion, but rather from this portion going to this portion. That is why we name this compound as 2,4-dimethylhexane and not 3,5-dimethylhexane. Another rule, if there are 2 or more different substituents. In our previous slide here, same substituent occurs more than once. But another here, 2 or more different substituents. Now, the rule is you need to list them in alphabetical order. Second, you number the chain from the end that gives the lower number to the substituent encountered first. It's just the same with the rule in our previous slide. And if there are different substituents in equivalent position on the opposite ends of the parent chain, give the substituent of lower alphabetical order the lower number. So, let's try to look into this example. So, we name it as 3-ethyl-5-methylheptane, not 3-methyl-5-ethylheptane. Why? Let's try to look into this by following the specific rule of IUPAC. Now, first, we will locate the longest parent alkane, and this one. And we number it 1, 2, 3, 4, 5, 6, 7. So that means 7 carbons. That is why the name is heptane. Heptane. And based on the rules, we start here counting because the positions on opposite ends of the parent chain give the substituent of lower alphabetical order the lower number. So, let's focus our attention first on the substituents. What is the name of the substituent? This is methyl. And this because of one carbon, meth. This one, we have carbon number 1, carbon number 2 substituent. So, supposed to be the name is ethane. But since it is substituent, then therefore, we drop the A and E and then we attach the YL. That is why the name is ethyl. So, this is the methyl substituent. This is the ethyl substituent. Based on the rule, the substituent of lower alphabetical order, the lower the number. So, in alphabet, of course, letter E of ethyl comes first before the M of methyl, right? So, that is why we need to number or provide the lowest number of the longest parent alkane carbon in this portion, not in this portion. Why? Because we encountered ethyl first here. Because in alphabetical, ethyl comes first than the methyl. I mean, E comes first than M. Thus, we give the lowest number in this portion, not in this portion. That is why we named this as 3-ethyl, meaning the ethyl substituent is attached in the carbon number 2 of the longest alkane. 5-methyl because methyl is attached in the carbon number 5 of the longest alkane. And heptane because the longest alkane has 7 carbons. That is why it's hept. And we add ane. That is why it's heptane. Again, the name of this compound is 3-ethyl-5-methylheptane, not 3-methyl-5-ethylheptane, because we follow the rules of this compound with two or more different substituents. The last rule, do not include the prefixes di, tri, tetra, and so on, or the hyphenated prefixes sec, tert in alphabetizing. That means we alphabetize the names of substituents first and then insert these prefixes. Like for example, in this compound, we have 4-ethyl 2,2-dimethylhexane. So now, again, let's try to look into this. 4-ethyl 2,2-dimethyl. Remember, we do not include the di here in alphabetizing. Okay? We focus our attention in alphabetizing only on the M of methyl and E of ethyl, not by the D. Okay? So, that means, still, in alphabetical, we have 4-ethyl 2,2-dimethylhexane, not 2,2-dimethyl 4-ethylhexane. Okay? Because of this rule. There is another way of naming alkanes using common names. So, this common names is actually in this older system. So, we have rule number 1. The number of carbon atoms determines the name. So, we count how many number of carbon atoms in the compound, and that determines the name of it. So, later I will discuss further. The second one, the first 3 alkanes are methane, ethane, and propane. So, all alkanes of formula CH4H10 are called butanes. All those of formula C5H12 are called pentanes. So, for alkanes beyond propane, ISO shows that one end of an otherwise unbranched chain terminates in CH3-2CH. This formula gives us an idea that CH3 here, the subscript here gives us an idea that we have 2 CH3. Okay? So, for more complex alkanes, we use IUPAC system already. So, for example, we have isobutane. Okay? So, the name is butane. Why? Because butane has 4 carbons. So, 1, 2, 3, 4. Okay? So, supposed to be the carbon number of this structure is 1, 2, 3, 4. And how many hydrogens? 3, 6, 9, 10. And that is CH4H10. All of CH4H10 are called butanes. All CH5H12 are called pentanes. But for alkanes beyond propane, okay, or 3 carbons, we use iso. That gives us an idea that the structure, of course, at one end of an otherwise unbranched chain ends with CH3 to CH. Like for example, this one, the color red. CH3, how many CH3? 1, 2, and 1 CH. So this is iso. Another one, iso, because 2 CH3s and 1 CH. This is iso. Why naging isobutane? Because isobutane, iso because of this structure, and butane because of 4 carbons. This one, isopentane, iso because of this structure, and 5 carbons. 1, 2, 3, 4, 5. But more complex alkanes, as what I've said earlier, we use already IUPAC system. Now, in this slide, we have cycloalkanes. Usually, cycloalkanes are cyclic hydrocarbons. Cyclo, that means it forms a circle, but not perfect circle in mathematics, but in at least they are joined to form a ring. So that's why cyclic hydrocarbons are hydrocarbons that contain carbon atoms joined to form a ring. And your cycloalkane, it's a cyclic hydrocarbon in which all carbons of the ring are saturated. Again, going back to what I have said earlier, saturated because it actually contains 4 bondings of carbon. So, cycloalkanes of ring, sizes ranging from 3 to over 30 carbon atoms that are actually found in nature. Like, for example, extracted from plants and from animals. So, 5-membered like your cyclopentane and 6-membered cyclohexane rings are especially abundant in nature. So, this structure of your cyclopentane and your cyclohexane are abundant in nature. In naming cycloalkanes, the prefix name of the corresponding open chain alkane with cyclo and the name each substituent on the ring. Second, if there is only one substituent on the ring, there is no need to give it a location number. If there are 2 substituents, number the ring beginning with a substituent of lower alphabetical order. The same also in naming simple alkanes. We follow in alphabetical order. So let us give the name for this letter A and this one for letter B. So let's focus our attention first in letter A, which is isopropyl cyclopentane. So, knowing, of course, we have, if we count the carbon of this structure, it has 8 carbons. So, let's try to count. 1, 2, 3, 4, 5, 6, 7, 8. It has 8 carbons with 16 hydrogens attached on it. Because there is only one substituent, this one, because of one substituent, there is no need to number the atoms of the ring. Thus, the IUPAC name of this cycloalkane is isopropyl cyclopentane. Cyclopentane because this parent is cyclic in nature, in structure, and it has 1, 2, 3, 4, 5. 5 carbons. Penta. So 5. So cyclopentane. Why is it isopropyl? Because this is 1, 2, 3. 3 carbons, that is prop. Why is it iso? Because it contains 2 CH3 and 1 CH. So let's move on into the physical properties of alkanes and cycloalkanes. So the most important physical property of alkanes and cycloalkanes is their almost complete lack of polarity. Why? Because the electronegativity difference between carbon and hydrogen is 2.5 minus 2.1 is 0.4 on the Pauling scale. So given this small difference, 0.4, we classify a C and H bond as non-polar covalent. Alkanes are non-polar compounds, and the only interaction between their molecules are the very weak London dispersion forces. That means the connection between carbon and hydrogen is very weak. That is why it's easier to break during chemical reaction. In terms of melting and boiling points of alkanes and cycloalkanes, the boiling point of alkanes are lower than those of almost any other type of compound with the same molecular weight. So, in general, both boiling point and melting points of alkanes increase with increasing molecular weight. So, let us focus our attention in this molecular weight of methane. It's 16 AMU. So, as the alkane increase in molecular weight, then the boiling point and the melting point also increases. That means once the molecular weight increase, your melting point and your boiling point increases. So that means it is directly proportional with the molecular weight of your compound. Again, directly proportional to the molecular weight of your compound, your melting point and your boiling point. Further, alkanes containing 1 to 4 carbons are gases at room temperature. Alkanes containing 5 to 17 carbons are colorless liquids. High molecular weight alkanes, those containing 18 or more carbons, are white, waxy solids. Several plant waxes are high molecular weight alkanes. So the wax found in an apple skins, for example, is an unbranched alkane with the molecular formula of C27H56. Paraffin wax, which is a mixture of high molecular weight alkanes, is used for wax candles, in lubricants, and to seal home canned jams, jellies, and other preservatives. Petrolatum, So, named because it is derived from the petroleum refinery. And it is known as a liquid mixture of higher molecular weight alkanes. And it is sold as mineral oil and Vaseline, and is used as an ointment base in pharmaceuticals and cosmetics, and as a lubricant and rust preventive. Now we know already the application of these alkanes that are very available in our households. Another property, physical property of alkanes that are constitutional isomers are different compounds and have different physical and chemical properties. Like, just for example, in this table, we have hexane here, and we have 2,2-dimethyl butane. Okay, so these are this is the cloud structure of your hexane and your 2,2-dimethyl butane, and these are the line angle formula of your compounds here. As what you observe, these are constitutional isomers. They have the same molecular weight, but they have different in boiling points because they have also different physical and chemical properties. In case of the solubility and density of alkanes, because alkanes are non-polar compounds, they are not soluble in water, which dissolves only ionic and polar compounds. Recall that in our college days, or maybe in our previous lectures, that water is a polar substance and that its molecule associate with one another through hydrogen bonding. Alkanes, on the other hand, do not dissolve in water because they cannot form hydrogen bonds with water. Alkanes, however, are soluble in each other. For an example, of course, like dissolves like. Alkanes are also soluble in other non-polar organic compounds such as toluene and diethyl ether. In terms of density, the average density of liquid alkanes that is listed already in our previous slide, where this one, the density of alkanes listed here is about 0.7 grams per ml. That of higher molecular weight alkanes is about 0.8 grams per ml. All liquid and solid alkanes are less dense than water, which is 1 grams per ml. And because they are insoluble in water, they float on water. So that's why if we have experiments in lab setting, when we mix water and an alkane, the possibility is that your alkane will float because it is lighter than your water. Let's move on to the reactions of alkanes. So, First, we have oxidation, or also known as combustion. So, reaction with oxygen. So, oxidation of hydrocarbons, including alkanes and cycloalkanes, is the basis of their use as energy source for heat, like natural gas, liquefied petroleum gas, or the LPG that we use in our houses, and fuel, or a fuel oil, and power for, like, for example, gasoline, diesel, and aviation fuel. So the following are balance equation here. The balance equation for the complete combustion of methane. So remember that methane, or the CH4, is the major component of the natural gas, and propane is the major component of LPG and bottled gas. So the heat liberated when an alkane is oxidized to carbon dioxide and water is called heat of combustion. So in this equation here, we can observe, in addition of oxygen for methane, it will react forming carbon dioxide and water in at the same time, and energy in a form of kilocalorie per molar. So while propane here, if it will react to the oxygen, then therefore it will produce again carbon dioxide, water, and energy. Another reaction is the reaction in halogens, or with halogens, or we call it halogenation. So if we mix methane with chlorine or bromine in the dark at room temperature, nothing will happen. But if, however, we heat the mixture to 100 degrees Celsius or higher, or expose it to direct light, a reaction begins at once. So the products of the reaction between methane and chlorine are chloromethane and hydrogen chloride. What occurs is a constitution reaction. In this case here, the substitution of chlorine for hydrogen in methane. Okay? So there is a substitution of chlorine for hydrogen in methane with the presence of heat or light. On the other hand, if chloromethane is allowed to react with more chlorine, of course, further chlorination will produce a mixture of dichloromethane. This one, the dichloromethane, trichloromethane, and tetrachloromethane, if it will allow reactions. What I mean is that when we continuously react the products of halogenation, it will form dichloromethane, so on, trichloromethane, and tetrachloromethane. So in this last equation, the reagent is Cl2, is placed over the reaction, or in this portion, over the reaction arrow, and the equivalent amount of HCl formed is not shown. So placing reagents over reaction arrows or omitting byproducts is commonly done to save space. We derive IUPAC names of haloalkanes by naming the halogen atom as a substituent, like the fluoro, the chloro, bromo, and iodo, and we alphabetize it along with other substituents. Common names, on the other hand, consist of the common name of the alkyl group followed by the name of the halogen, let's say the chloride, the bromide, and the iodo. So, as a separate word in the name. Dichloromethane, it's a methylene chloride, is a widely used solvent for organic compounds. In this slide, it gives us an idea about the chlorofluorocarbons. Chlorofluorocarbons, or the CFC, are manufactured under the trade name Freon. The CFCs are non-toxic, non-flammable, odorless, and non-corrosive. So among the CFCs most widely used were the CCl3F, or the Freon 11, and the CCl2F2, or the Freon 12. So CFCs were used as heat transfer agents in refrigeration systems, industrial cleaning solvents, to prepare surfaces for coating and to remove cutting oils from millings, and propellants for aerosol sprays. And we all know that chlorofluorocarbons are very important in studying environmental science, and especially in protecting our environment, because chlorofluorocarbons are the one that destroys our ozone layer. Thus, there are efforts to remove these chlorofluorocarbons in aerosol sprays, to propel these aerosol sprays, and at the same time in our refrigeration systems, in our refrigerator before, because chlorofluorocarbons has a negative effect in our ozone layers. That is why the CFC replacements, which is the chlorofluorocarbons, cause, because of this causative destruction of Earth's atmosphere, or particularly the stratospheric ozone layer, the most prominent replacements are the hydrofluorocarbons, the HFCs, and the hydrochlorofluorocarbons. So these compounds are chemically more reactive than CFCs and are destroyed before it reaches into our atmosphere, or particularly in the stratosphere where our ozone layer is located. That is why it is much safer than the chlorofluorocarbons. So, what are the sources of alkanes? Of course, primarily, it is natural gas, which is 90 to 95% of methane, and 5 to 10% ethane, and at the same time a mixture of other relatively low boiling alkanes, chiefly of course the propane, the butane in our butane stoves, and 2-methyl propane. Also in petroleum, we all know that petroleum is a thick viscous liquid mixture of thousands of compounds, most of them hydrocarbons formed from the decomposition of marine plants and animals. We reached already into the end of my presentation, so thank you very much for your kind attention. God bless everyone.